So, good morning, everybody, and welcome to our 9th edition of the Code of the Month of CASTIEL 2. We have the pleasure to host today the HiDALGO2 COE, which will present their urban air project, which is a complete workflow for modeling airflow and transport of pollutants in cities, and could be used to guide urban planning, but also to prevent hazards. So the presentation will be introduced by Zoltán Horváth, and then László Kornei and Matás Konstanz will give some more insight on specific aspects of the tool chain, or are from the Székely István University in Győr in Hungary. So please, Zoltán, the floor is yours. So one thing, we will have a Q&A session after the presentation, so you can type it in either into the chat or there is a specific questions Q&A tool in the controls. Then we will do that after the talk. So now, please, Zoltán. Zoltán, you seem to be muted.
Okay, thank you. Thank you for the reminder. So, welcome everyone to our meeting. It's our pleasure to introduce you our loved codes. We work a lot with these codes, and it's a pleasure to us to present it to this audience. We are from the Székely István University from Győr, Hungary. I'm a mathematician, basically, and computer scientist. László, can you tell some words of you? So,
hello, nice to meet you. I'm László Kornei. I'm basically a physicist, and I've been doing my PhD in physics, but also do mathematical, programming and software development, and teach mathematics at this university, and I am responsible for the UAP form, so the open form based component of the workflow. Thank you.
Okay, Matás.
Hello, so I'm Matás Constant, and I'm a programmer at the same university. I have a background in mathematics.
Okay, many thanks. So we are proud members of the HiDALGO2 consortium, which is a Centre of Excellence of the Euro-HPC joint undertaking. I can see time is getting late, so it will be just a very quick introduction of the HiDALGO2. This is a Center of Excellence for tackling global challenges with HPC and AI technologies. So we are developing basic technologies and also some use cases. We have environmental use cases. Most of them are basically CFD applications. So there are very good synergy between the use cases. We are for the urban air pollution and in general an urban air project. University of Strasbourg has been developing urban building modeling. PSNC from Poznań, Poland, they are developing renewable energy systems to predict the produced energy by renewable energy systems, depending on the weather and other conditions. Meteogrid company in Madrid, Spain, they have been developing the white fires use case, which simulates propagating fire and smoke from the forest fires. And FAU, Friedrich-Alexander-Universität Erlangen, they are developing with lattice Boltzmann method transportation of materials in water. And a preface to this talk for today is graphically summarized by this picture. We have a three-dimensional simulation for the urban airflow for an entire city that is something like 5 or 6 kilometer by 6 kilometer by 1 kilometer domain with real three-dimensional urban geometry. And we simulate the airflow, and then we simulate passive scalars, or we solve the advection diffusion equation under environmental conditions for the emission propagation. This is for the air quality, or we compute low zone wind comfort, some KPIs from the airflow. So, and we visualize it, and we want to make it faster than real time and very high resolution. So, in a nutshell, this is our urban air project. So, in this talk, I'd like to first give you some motivation, our urban environmental challenges, and the HPC solutions. This is a motivation section with the goals. And then I will show you an overview of our UAP, the Urban Air Project application, and the related HPC codes. So we have more general codes. We are solving more general systems, not only the air pollution and airflow problems, but our codes are suitable, and actually we do solve problems for industry. So we show you the Matso portal, which is a web interface for HPC job configuration, deployment, and execution. And this is the skeleton of the workflow of the UAP. And then I show you overview on the OpenFOAM and RedSim, two CFD codes for the solution of Navier-Stokes equations. OpenFOAM, probably you know, a well-known open code for that purposes, and RedSim is our native multi-GPU code with a flexible API. CFD rendering is a general tool for visualization of scalar and vector fields. And for HPC, to visualize HPC results on your web, that is, for example, on your laptop. Conclusion, after the conclusions and further work, you will get two demonstrations. The first by Laszlo about the portal and with the OpenFOAM, and then with Mátyás with the RedSim and CFDR. So, what are the challenges that we want to tackle? The first is the air pollution, and this is very critical in many cardiovascular diseases, and as a consequence of the bad air quality, each year 7 million people or something like that deaths are attributable to bad air quality, and several cities were or currently still are very much polluted. EU has some regulations. Each country has to report according to the regulatory regulations the status of the air quality in their country. The second part of the second challenge are the accidental releases. So the accidental or intentional toxic gases, point sources, or very much located to a certain small area of a city. There are some releases, and and it propagates under the weather conditions, the real weather conditions. We simulate the propagation, dispersion of the released gas in the three-dimensional urban domain. 1 year ago, perhaps you remember that there was a very massive fire in Hamburg, and very quickly the citizens had to be alerted to close the windows, and because it was really a harmful gas that was propagated. So very quickly we have to make a simulation if you want to support the mayor with the information of the propagation. We have to be faster than real time with the simulation under urban geometry and accurate. So we can already feel somehow that HPC is needed for a certain part of this topic. The pedestrian wind comfort seems the less important, but actually the wind discomfort can result in dangerous situations, in particular near tall buildings, because at the corners, in particular at the corners, or the channel effect implies that the wind speed near the foot of the tall houses, in particular at very tall houses, are much higher than the average speed of the wind in the city. Much high. It can be much higher, and there is a famous building in New York City, on which the Flatiron, on which picture you can see to the right, and there is a very nice video from the 93 on the YouTube that shows us the crazy situations that they called it crazy wind, that much higher. So we want to prevent these situations. So when planning the new buildings, it's now, for example, in the Netherlands, that standard has to be followed to prevent this discomfort. Okay. So what are the methodologies to tackle these problems or mitigate these challenges of the environment? Computational tools for the analysis at very high resolution, reporting tool according to the EU regulations, full year simulation. It's really a demanding task. Develop decision-making tools, real-time digital twin, that is live simulation that assimilates the sensor data continuously to the simulation, and design tool for urban building planning. So for these tasks, we have been developed the UAP, the urban air pollution workflow, and we have to provide it to non-HPC experts as well. This is a serious point in the solution, because sometimes city hall employees will apply our tools, hopefully. And so easy to use softwares, HPC softwares, and the portal, and these are our CFD codes, the open from the Red Cement CFDR that shortly I introduce you. We shall go to more in details. This is just one quick overview of the workflow. Here you can see in this blue box the airflow. This is in the core of the urban air pollution application. And for that, we need regional weather simulation or observations, measurements. We need information on the emission if we want to go for the air quality. And there are several databases to be integrated to our system. And there are some other points to be addressed, for example, also mid-comfort computation. That is with HPC, we are computing from time step to time step. We are simulating unsteady simulations. So 10 million unknowns per time step. So it's very demanding. Also, the evaluation of them needs high performance data analytics, HPDA. This is a very quick overview of our workflow. On the left image, you can see just a snapshot of our workflow. This denotes something that on the web you can configure the full job with clicking and giving and writing some details into some cells. Then from the OpenStreetMap, we generate the geometry, the three-dimensional geometry. OpenStreetMap does contain three-dimensional information on the buildings as well. So not only the polygonal of the buildings are provided, but also the height of the building and the shape of the roof. And from this, we create the geometry, we mesh it, that is, we subdivide the airflow domain into small cells, and for the numerical approximation, we run the simulation and visualize the results. This all can be done from the portal, and Laszlo will demonstrate it with OpenFOAM. Just a quick overview, because you will see these pictures in the demonstration, that there is an authentication. You can give the CCAN API key to you to upload data and to handle data in the CCAN repository. You can select, you can configure the HPC system that you want to, on which you want to run your system. You can copy here the SSH key, and then you will run actually with your key on Lumi, for example. I skip because the shortage of time. I skip these files because Laszlo will show us these steps. This is the dashboard of the simulations, and we can see that some jobs have been already converged. Some jobs for certain reasons failed. We can see the messages from the computer also in a log file. And Laszlo solved the continuous CI/CD and the containerization from the portal subtasks as well. This is just a quick overview that you can write here the numbers, and behind there are blueprints written in Tosca language, and in this way you can execute the simulations and visualize, and everything is written in Tosca language and ran from the portal. The CFD codes in the UAP are the OpenFOAM. We saw with the PimpleFOAM, the SimpleFOAM solvers of the OpenFOAM, the 3D incompressible Navier-Stokes equations, URANS and RANS, respectively. That is finite volume methods on unstructured meshes. The code has been optimized, and we have a pretty good parallel efficiency result for the whole geometry, and we ran it for within the FAIRMOD is the Forum for Air Quality Modeling in Europe. This is a European initiative and collaboration of different air quality modeling groups that support the regulatory purposes of the countries, and we tested our approaches together and wrote a joint paper. I introduced you RedSim. I'd like to tell you only in addition to what I told you that it has a reduced order model. This is why we call it RedSim, reduced simulation, with the proper orthogonal decomposition and the pod combined with a discrete empirical interpolation method. So we wanted to catch all points in mathematical algorithms as well to accelerate the simulations. One very recent result that Mátyás programmed is that the HPC code, the same code, exactly the same code, runs already on PCs, personal PCs, that is on a Mac or a laptop with Microsoft Windows as well. The same code. So these custom machines are already very strong, and engineers may use first and try it and go with the same code and the same API to HPC machines when needed. So the UAP with the OpenFOAM overview can be seen here. Actually, I told you these details, so maybe I can go to the next slide. And here, this was a hackathon for the validation. You can see here in orange the measurements, and in blue the OpenFOAM computations. This is for 1 month, and above this is for 1 day, May 6. The results, we can see that it is pretty good, the agreement between the measurements and the computations, but still we don't capture some peaks, so we have to improve our atmospheric model. And on our local cluster, 1 full year was simulated within less than 20 days on Solyom, on less than 400 cores. So this was for the convenience, we ran it on our local cluster, the full year simulation, and it was pretty good. These are the parallel efficiency results of the OpenFOAM, which is pretty good, I think, for a very unstructured, non-balanced mesh. And some words about the RedSim and the CFDR. The RedSim is a native multi-GPU CFD solver written in CUDA, so this is for NVIDIA GPUs. And CFDR is the visualization, and the CFDR compiled on the HPC, and only the necessary data for the visualization are coming to your website, to your browser, and we have a Lua API. Mátyás will show this in the demonstration. We have several licenses, but for free you can test the RedSim if you wish. Just send us an email and you will get the one CPU node for testing purposes, all with full functionality. The same code runs also for the same algorithm runs with MPI on clusters, and also the GPU code is the same. For the GPU code, we don't have a free license yet. So to save time for the demonstrations, let me go to very quickly on these slides. This is a very compact code what Mátyás created for the RedSim. and we don't use unnecessary other frameworks, other libraries. So it's compact and could run very efficiently on and can be compiled within seconds on any machines, for example, Vega or other machines of the EuroHPC. So this is an industrial test problem of the for the acoustics of the X-hose pipe of a car, and here below you can see the agreement between the measurements and disagreement with the measurements and the computations. So engineers said that this is a pretty good agreement between the results. And maybe the last slide about this introduction are the benchmark results. So for the 2D Karman vertex, we got with 8 GPUs, almost 99% of parallel efficiency on 300 million of cells. And for the urban airflow, this was a structured mesh, nice mesh. And this down for the urban airflow, we had a less structured mesh, but with 10 million cells, we are somewhere in between the 2D Karman vertex values here and the 60% of parallel efficiency is pretty good. Later, we want to go for higher resolution meshes, and we get even higher parallel efficiency with the GPUs for the city simulations. So we could simulate 1 full year with unsteady simulations within 3 weeks on a very small cluster. We have a digital twin visualization of the results as well. So we have this live visualization of the results, and we have the portal, and from the web you can submit HPC jobs, and we want to optimize very significantly and couple our codes and put more physics, more atmospheric physics and chemistry into the codes, and coupled with other use cases, in particular with the other use cases of the HiDALGO project. So let's turn now on to the demonstrations, and if you have questions after the demonstrations, I would be very glad to answer your questions. So Laszlo, the floor is yours for the demo of the portal and the open form.
Thank you, Zoltán. Let me show my screen. I hope you can see my screen. I will be very quick. What I would want to present is how to import a custom geometry into UAP foam, and then how to create a mesh, and how to create a simulation where there is, for example, some kind of hazard that is within the city, and emission pollution is coming from that single point. Okay, so this is very small one. So first, I will be selecting an area from OpenStreetMaps. This will be the latitude and longitude geometries, which will be copied to the clipboard. And afterwards, I am opening Blender, and in Blender, there is an extension called BLOSM. And with BLOSM, you can download these geometries to Blender. It will import almost everything, every geometry, including roads and buildings and green areas, and it also can import to ground. So after this, we can select the buildings. In this example, I will only use the building geometries of this suburban area of Stockholm. And after zipping it up, I am uploading it to the Matso CCAN. So the CCAN is a data repository, an open source data repository, which stores input and output data for our simulation. So after we are created this geometry and uploaded, we can use the portal. So I would want to just show you this, how this is done. So we go to experiments, manage instance, and from the applications, there are a lot of applications in the portal. Actually, you can, so if you're an application developer, you can also use the portal to develop your own application with the Tosca language that Zoltán describes. So I am selecting Snappy, and I've already configured the Stockholm mesh generation. Okay, so we do have integration in progress. So I could select MPI-CH for the Lumi or OpenMPI for other HPC machines. We use OpenMPI for the Shoyom, but this is not yet fully integrated. And here you can select from the Matso CCAN, from the input geometries, the Stockholm geometry, which we have just created or has been created beforehand. And this will be the mesh repository that is also in the Matso CCAN. Here will be the mesh uploaded. There are some advanced settings, and in the advanced settings, here you can set some kind of parameters for these meshings, for example, maximum cell size and refinements and so on. Okay, so if you're ready with this, you can update or submit it, and then go to execute, select the application. You can select the instance, the configuration that we have just created, and then we can select the HPC and the partition. Okay, and then you can click on execute. This will come to this part where it will be generated, this mesh will be generated. Okay, so as this runs and this finishes, there will be a mesh generated and uploaded to the Matso CCAN. Okay, so what does the mesh look like? So I've downloaded it. Of course, you can download it and open it, for example, in ANSA. This is a usual Snappy X mesh open form mesh. You can see the buildings, the ground, and the volumetric elements. I marked 3 points, and this will be the point source we will be simulating, and 2 others are probe points. So what you can do with this one, let's go to back to the portal, manage instance. We can use the UAP form. This is the open form based urban air pollution, and I've already configured this instance. Here you can also select the image, and here you can select the mesh. Well, this is just what has been generated beforehand. And here you can select what kind of emission you have. You can have only wind comfort, then you will have no emission, or EMI-based. If you have some kind of traffic, you can generate these EMI files, which are cell-based source terms, and we can select the point source. Okay, and in this advanced settings, for example, we can generate this point source, the location of the point source, and the rate. This is the per second volumetric unit. Okay, after this one, we can also submit it the same way, for example, on the Shoyam. Okay, so if this is the after the execution, the simulation will be shown on the dashboard, and the results will be uploaded to the UAP form results data set on the CAN. So you can actually download these results to your computer and look at them. These are N-site-based results, and these you can open in, for example, ParaView, and look at, for example, the velocity magnitude across this region with the predefined configuration, or you can look at how the specified pollution source is propagated across the city if you have a wind that this is a constant wind right now. Okay, thank you very much. This is all I wanted to show you. If you have questions, then please feel free to ask anything. Thank you.
I will make a demo now, basically on how and I will make it quick to make up for the time we've lost, on what is our workflow exactly for generating geometry from an OpenStreetMap region and simulating on it. So for example, if you go here in Stockholm, so this place here is Stockholm basically, and I'm going to go here and I'm going to basically export a certain region here. So I can go here and export, manually select different area, and let's say I want to export something like a tiny bit of a smaller region. Let's say this region seems relatively fine. So let's say I want to do a simulation of this region. I will just hit export here. I will get a file that I can then just put on my desktop. Let's rename this file to test1.osm in this case. And yeah, once we have this test1.osm file, we can use a very simple, I'm going to use a very simple SCP command here to just copy this file to our local cluster, as you can see here. So I'm now copying this file to our local cluster by a simple SCP command. Sorry, need to first change directory. Yeah, so we can copy this file to our cluster here. So this has been copied. Now that I'm on my cluster, I can just launch we have a Python script which basically automates some part of our workflow, but we're still using Lua as our main scripting language. So right now I can just go Python mbp run test1.osm. This will basically launch our software. So there are multiple stages to this whole thing, and I will narrate a bit while this is running. Essentially, the idea is that first, we are taking the OpenStreetMap geometry that we have downloaded from online, and we are extracting basically 2D plan of the houses, and using certain OpenStreetMap metadata, we're essentially doing a 3D reconstruction of the data. So we're basically building up a 3D mesh. We're then using a meshing software. So once we have this 3D shell, basically, we're using a meshing software, in this case, STEDGAN. And as we can see here in the simulation, our mesh is currently somewhere around 500,000 tetrahedras. And now we are using our very fast GP solver, which is, as you can see here, this is the amount of seconds for our simulation. So it's already at like 198 seconds. And yeah, the simulation has been finished. So once the simulation has been finished, I just get a link here with different statistics. So our OpenStreetMap processing time was like 3 seconds. Our meshing time was like 5 seconds. Our mesh visualization time, which is just an intermediate step, 13 seconds. The most important part, the simulation time was 20 seconds. And since we were simulating 200 seconds in real time, that means that this simulation here was 10 times faster than real time, basically. And the visualization time is basically non-existent. It's just a couple of milliseconds. So if we open this link here, so let's open the link and let's check our simulation. So as you can see, here I can see basically the houses that I have selected before, and I can roam around with the camera a bit, and I can basically check my simulation. So for example, I can go ahead in time, go backwards in time a bit, and we can see all 200 seconds simulated. So I can also, for example, change the range of the velocity. So if I'm more interested between the values between 0 and 3, I can just clamp it. I can also put in a vector field so I can see like more interestingly what's happening. Of course, this is like a lower resolution mesh because for the sake of demo, I just wanted to make something very simple for this demo. But of course, we can simulate with RedSim, with Zoltan, we simulated up to 80 million cells, but even further, I think the furthest we went is 500 million cells technically for a 2D problem. But the point is that this is just a simple demo. That's why the simulation is a bit rough. And we can also check the different aspects of the simulation, like the density. So the density profile is kind of interesting for the simulation, how it changes over time. The pressure, of course, as well. And yeah, we can also check, for example, the laws on wind comfort. So we have different like color maps, and if we go on the laws on wind comfort map, then we basically get a nice chart telling us like what percentage of the city is basically in a occasional sitting kind of state for wind comfort, and I can scrub through time and just see how this changes. Of course, we have a much more interesting examples on our website, like Zoltan mentioned. So if you go on our website here, as you can see, with RedSim, we also simulated simulations for mufflers and different like kinds of components. If you go on our overview here, we can also see, for example, that we can simulate much larger regions. So here you can see this is a much larger city region, of course, and much more dense and much more interesting. But it still takes about the same time to simulate, fortunately. So another thing with RedSim, which is interesting, which Zoltan alluded before, is that we have this whole setup basically where we only have one command to run every time. It's just RedSim CUDA or RedSim MPI if you're using the MPI version, then the Lua script. And basically this Lua script is kind of like a configuration file, but on steroids. So it's basically a really expressive way of like telling what to do while simulating everything. And this both works, this setup for MPI programs. If we're using an MPI program, we have a master-slave setup basically, where only the master node is executing the Lua script and it's basically giving instruction on the slave nodes on what to do exactly. So if we go here, for example, on running applications, application examples, and we check, for example, the Karman example, we simulated like a Karman vortex example, and I can basically do a walkthrough through this process. So in our Lua scripting language, for example, the first thing we do here, as can be seen, is we initialize our framework. Then we basically define a PID, property ID table. Then we find a list of holes. And so basically we only have one hole in this geometry, and we have a function thanks to which we can basically generate a geometry. So for example, if I say rsim.jo.grid2d, this is going to generate a grid basically of like 600 times 200 cells, and it's going to place a hole in the middle here based on how I defined it. It's going to assign PIDs on the left, right, top, bottom, and also on the holes. And once I have those PIDs and these meshes set up, I can just call rsim.solve.euler, which is going to solve this system for the Euler equations. And perhaps most notably, we can basically give an initial condition. We can actually specify an initial condition and boundary condition as a Lua script. And then we do essentially some very heavy optimization on that Lua code. We turn it into bytecode and everything in order to call this code from C++. Now, our main code base is very heavy C++, and the Lua script layer basically is optimized as much as humanly possible, basically to not make it not make the simulation slow, because as we both know, as we all know, basically garbage collected languages and anything that has even garbage collection is incredibly slow these days, undeniably. So we really did our best basically to abstract away as much of the C++ code base as we could into the Lua scripts, but it's still very efficient because essentially all the handles and all of the different objects I'm creating in Lua is basically just on a big handle that has no that we can't access directly. So everything is heavily optimized in this way. But we have multiple examples like the SOD shock tube test problem, a canyon for like urban air pollution, and even a exhaust pipe with a very intensive workload dispatch in this case. As you can see, this is a pretty intense simulation. Now, one of the interesting things is that we also have a digital twin integration for RedSim, which means that we can basically change the boundary condition and see the results updating live. And we have multiple digital twins developed. We have one for urban air pollution, but we also did one for a diesel motor, where we could basically just change one of the components, like the pressure, and we would see the results updated live. So yeah, hopefully I'm still in time, and I will give Zoltan the presentation back.
Thank you, Matyas, and everyone. Yeah, it's my screen. I have just now the opportunity to thank the HiDALGO2 project for the support, and also the Hungarian NCC for providing HPC resources to our work. So thank you, and if you have any questions now or later, please send us an email. Also, if you want to test the codes, also in that case, we can send it to you after an NDA. We don't have yet a general license. It's in progress with the legal department of the university, but we have not converged yet with these licenses. But under an NDA, the one node plus the full Lua script, Lua API will be sent to you. Thank you so much.
So thank you very much, Zoltan, Laszlo, and Matyas for this very interesting and detailed presentation. And